This video will cover 2.2, water. Understandings, application, and skills that will be covered in this video. So we'll start with the general structure of water molecules. So water molecules are polar. So water is made up of two hydrogen atoms covalently bonded to one oxygen atom. So you have that oxygen atom that forms a covalent bond with one hydrogen atom and will form a second covalent bond with another hydrogen atom. There's also two pairs of unshared electrons, or lone electrons, on the oxygen atom, which will ultimately help create some of the properties that helps explain water's behavior. So the electrons in the covalent bonds are not shared equally. So not all covalent bonds share electrons equally. In this case, oxygen will have the greater pull on the electrons shared with hydrogen. So what this means is that the shared electrons will spend more time at the oxygen atom than the hydrogen atoms, because now they're spending more time at the oxygen rather than the hydrogen. This will now create charges around those atoms. So oxygen will gain a partial negative charge. It's not a full negative charge because it's not acquiring those electrons solely. It's still sharing them with hydrogen. So most of the time the oxygen atom will have a negative charge to it. Sometimes it won't. And to represent that partial negative charge, we use that Greek letter delta with a negative sign next to it to indicate a partial negative charge. Now, because those electrons are spending a lot more time at the oxygen than the hydrogen atoms now will gain a partial positive charge, which we can represent with that Greek letter delta with a positive sign next to it. So the difference in charge at the poles, and when we say poles, we mean like the two ends of the molecules. So, you can consider the top of the oxygen one pole and the bottom of the hydrogen another pole. And so we have two different charges that occur in different parts of the molecule. And ultimately, these differences in charges is what causes water to be polar. So the fact that water is polar will help it create these special types of bonds referred to as hydrogen bonds. So where do these hydrogen bonds come from? Well, the charge difference across the molecule, which we refer to as a dipole, will allow water to form weak associations with other molecules. So the slightly negative pole of water will attract the positive charges of other molecules. So basically the negative part of the molecule is going to interact with the positive charge on other molecules. And then the slightly positive pole of water will attract the negative charge of other molecules. Now, when the slightly positive charges of hydrogen on water are attracted to the slightly negative charges of oxygen, fluorine, and nitrogen, and these three atoms specifically, it will form a special type of interaction referred to as a hydrogen bond. Now, the hydrogen bond is demonstrated in this picture, in this diagram, between different water molecules. So you have and it's represented by these dashed lines. So you have the slightly positive charge of one hydrogen atom that forms this interaction with the slightly negative oxygen on another water molecule. And the same water molecule can form multiple hydrogen bonds. So these hydrogen bonds individually are weak, but they are a relatively strong intermolecular force due to the high electronegativity of oxygen, fluorine, and nitrogen. And individually, they are weak, but together, when you have many, 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 many hydrogen bonds being formed, they are strong. So it's a strength in numbers type thing. Now, hydrogen bonding is a theory, as hydrogen bonds cannot be directly observed, so nobody's ever looked at two water molecules and said, there is a hydrogen bond between them. But it's based on, this theory is based on observations made of water, and it can help explain the properties of water or how water behaves, such as the cohesive, thermal, adhesive, and solvent properties of water. So we can consider a theory correct if there is evidence for it, if it can predict behavior, has not been falsified, and helps explain natural phenomena. So in this case, hydrogen bonds can help explain how natural phenomena occurs. So we have some indication that this is most likely correct. So going through a number of the different properties of water and looking how they come about, we'll start with the cohesive properties of water. So we'll start with cohesion. So in those cohesive properties, this is where hydrogen bonds cause water molecules to stay close to each other. So this is water molecules forming hydrogen bonds with other water molecules. So collectively, these hydrogen bonds will hold the substance together. The water molecules are linked by multiple hydrogen bonds, in which the arrangement of the molecules is constantly changing. In other words, the hydrogen bonds are not static. They're always breaking and reforming. In transpiration, this is where water moves from the roots of a tree up the tree itself and into the leaves. The way a tree will move water from its roots to the leaves in this process of transpiration is that it will use these cohesive properties of water to form a column through the plant tissue referred to as the xylem, in which the tree will take advantage of these water molecules sticking together by hydrogen bonds. And then, so this will allow that water to travel these great distances up a tree, use of those cohesive properties. Trees will also use the adhesive properties of water to transport water from root to leaf as well. So the adhesive properties are basically that a result of water molecules now, and again, its ability to form hydrogen bonds. But in this case, with the adhesive properties, this is where water molecules will tend to stick to other molecules that are charged or polar. So now this is water molecules interacting with other charged molecules other than water. So again, individually, those hydrogen bonds are weak, but large numbers give adhesive forces great strength. And as I mentioned, this is useful in transpiration. So adhesion of water to cell walls by hydrogen helps counter the downward pull of gravity. So in that tree tissue itself, you'll have these adhesive properties or these water molecules basically sticking to the plant tissue as that water moves up the tree. Hydrogen bonds can also be used to explain the thermal properties of water, and these thermal properties will be divided into two categories. The first one being the specific heat capacity of water. So when we talk about a specific heat capacity of a substance, we're talking about the amount of heat or the quantity of heat needed for 1 gram of a substance to change its temperature by 1 degree Celsius. So this will vary from substance to substance, as some substances can retain heat better, or some substances need more heat to be put into it to raise that temperature by 1 degree Celsius. Now, water will have a high specific heat capacity, and this is relative to other materials. And relative to other materials, water will change its temperature less when it absorbs or loses a given amount of heat. So, if you ever watched a pot of water boil, it seems to take forever. And this is based on the fact that water can absorb a lot of heat before that temperature will start to increase. So it takes a long time for that water to boil. And even so, once that water is boiled, it will stay hot for a long time, as it will take a while for that energy to be released. So the reason for this high specific heat capacity comes down to, again, hydrogen bonds. So heat must be absorbed to be able to break those hydrogen bonds, and then heat gets released when hydrogen bonds reform as well. So where this becomes useful is that this will stabilize ocean temperatures and helps keep land temperatures within limits that permit life. So, our ocean temperatures don't fluctuate wildly between like very, very hot and very, very, very cold. So compared to other substances, the temperature of water remains fairly stable. So if you have a look at water temperature versus air temperature over the course of a day, that temperature in the air can start out, relatively warm and then drop dramatically and then increase dramatically during a day relative to water, whereas the temperature of water won't move very much as compared to the temperature of the air. It'll remain fairly stable compared to that air temperature. So another thermal property of water is that it has a high heat of vaporization. And when we talk about heat of vaporization, this is the quantity of heat that a liquid must absorb for 1 gram to be converted to the gaseous state. So this is how much heat must be put into a liquid to turn it from a liquid to a gas, and 1 gram of that substance. And so water has a high heat of vaporization, which is again due to the presence of those hydrogen bonds. Those hydrogen bonds again have to absorb energy in order for those hydrogen bonds to break. And this high heat of vaporization also causes water to have a high boiling point. So this is the reason why liquid water can exist over a broad range of temperatures. You can get liquid water anywhere from 5 degrees Celsius all the way up to 99 degrees Celsius. It's a very large range of temperatures. And the fact that water has this high heat of vaporization is what helps moderate Earth's climate and keeps things from wildly fluctuating. Water is also referred to as the universal solvent, and again, those hydrogen bonds can help explain that property. So when we talk about the solvent properties of water, when we talk about a solvent, we are talking about the dissolving agent or the liquid itself. So in this case, it would be water. The solute is the substance that is dissolved. So what is the solid thing that you're putting into the water to make it dissolve? And then when you add a solute to a solvent, you get a solution. So this is a liquid that is a homogeneous mixture of 2 or more substances. And then when you have water as the solvent, this is specifically referred to as an aqueous solution. So the polar nature of the water molecule will allow it to be attracted to ions and molecules with positive and negative charges. So it will allow a large number of substances to dissolve within it, why it's referred to as the universal solvent. So remember that, water is going to have that slightly positive charge at the hydrogens, and will have that slightly negative charge at the oxygen. And so if you have something like sodium chloride, that is going to break into sodium ions when dissolved in water. That positive charge on the sodium ion, is going to interact with that negative charge, or that slightly negative charge on the oxygen of water. And those chloride ions are going to want to interact with the slight positive charge on the hydrogen ion, because chloride will have a negative charge to it. So where this becomes useful is that you can have ions dissolved in the water component of blood, which is also referred to as plasma. And the fact that most biochemical reactions occur in aqueous solutions. So the cytoplasm, for example, would be considered an aqueous solution. So it's going to be mostly water in there. So ultimately, substances can be categorized as hydrophilic or hydrophobic. So if something is hydrophilic, it is going to be water-loving and will most likely be polar as well. So all substances that dissolve in water are hydrophilic, including polar molecules such as glucose, and particles with negative or positive charges such as chloride and sodium ions. Substances that water adheres to are also considered hydrophilic, such as cellulose. Cellulose is the one exception where it's considered hydrophobic, is non-polar, but will be hydrophilic. So it will interact with that water, but it won't dissolve in the water. For substances that are hydrophobic, these are water-fearing or will tend to be non-polar molecules. So molecules are considered hydrophobic if they do not have a positive or negative charge and are thus non-polar. So they have no overall positive or negative charge with them. Hydrophobic molecules will dissolve in other solvents that are hydrophobic. So for example, lipids found in the cell membrane are considered hydrophobic. They don't want to interact with that water. And so they will interact with each other instead, rather than the water. And so, as discussed previously, this is useful in forming that barrier of that cell membrane. Now, you could be asked to compare the thermal properties of water and compare that with those of methane. So when looking at the structure of water, it's going to be a polar molecule, and as a result can form hydrogen bonds. So because it is, a polar molecule, we have those slightly negative and slightly positive charges associated with it. As compared to something like methane, which has the formula of CH4, so we have carbon that is covalently bonded to 4 hydrogen atoms. The symmetry of the molecule means that methane is a non-polar molecule, and partly because it's non-polar, it cannot form hydrogen bonds. So the thermal property between these two molecules is pretty drastic. So, methane will have a lower freezing point. As a result, we'll have a much lower boiling point. It boils at minus 161 degrees Celsius. It has a very low heat capacity as compared to water. And has a very low vaporization point, or heat of vaporization, as compared to that of water, which is very, very high. So all of these difference in properties is attributed to the fact that water can form these hydrogen bonds, methane cannot. You also need to know about the use of water as a coolant in sweat. So sweat is mostly water. Water is that main component of sweat. Basically, when the water evaporates from the surface of the skin, so when you sweat, you basically get a layer of like water that forms on your skin. And as that water starts to evaporate, it is going to take heat, which is the heat from your skin, that will cause it to go from a liquid state into that gas state. When it starts to evaporate from the surface of the skin, it takes that heat with it. And then with the loss of that heat energy, the skin feels cool, or it's how you keep relatively cool. And lastly, you need to know about the transport of materials in blood. So the transport of essential molecules in the blood will depend on their solubility. So water-soluble substances will travel freely in the blood, while water-insoluble substances cannot. So in general, you have water-soluble substances, such as like sodium chloride, for example, which is an ionic compound that dissolves as sodium ions and chloride ions, which can be carried in the blood plasma, that water component of the blood, pretty easily. With amino acids, they have both positive and negative charges. So the negative charge, comes from the carboxyl group, while the positive charge will come from the amino group. And so it can be carried in the blood plasma. Just the R group can determine whether it's hydrophobic or a hydrophilic amino acid, but all amino acids in the end can be carried in the blood plasma. And glucose is a polar molecule, so it can dissolve in water and be transported in that blood plasma easily. Examples of substances that are insoluble and cannot be transported directly in the blood would be something like oxygen, for example, which is a small non-polar molecule that can dissolve in blood plasma in small amounts. So in some amounts it is soluble, but it's going to be mostly transported by red blood cells by that molecule hemoglobin. So it has a protein that will carry it around in the body to where it's needed. So with most water-insoluble substances, it has to be carried by something else. So for example, like fat molecules, lipids, for example, these are non-polar and must be carried inside a lipoprotein. So a lipoprotein complex is basically a single layer of phospholipids. So in the diagram, it shows this lipoprotein complex. So you can see the phosphate heads, which are represented by the purple circles. And then these yellow lines pointing inwards are the hydrocarbon tails. So those hydrophobic tails will point inward, creating a hydrophobic environment for those lipids to be transported. Cholesterol is also transported in these lipoprotein complexes. Because of the large hydrophobic region of the molecule, it makes it insoluble in water, and so it must be transported in these lipoprotein complexes. So this is the end of the video for 2.2, water.